So I work with graphs and networks, and the reason I like these types of structures is because they allow me to model very kind of different phenomena in different types of domains with a common underlying mathematical structure. So if you want to understand how Hollywood actors collaborate together in different movies, if you want to take people and understand how they are related to one another, or if you would like to take molecules in human cells to understand how they come together physically in our bodies to do various functions and give rise to life, all these types of different problems and many others can be modeled by the same underlying mathematical structure, which is a set of nodes, a set of vertices, and a set of connections between them. So down here is my little graph on 4 nodes and 4 connections. And of course, if you have this type of data, then you can start asking yourself what kind of machine learning tasks are typical to do over this type of data. And I give you a few examples here. So you can think about node classification, where essentially you would think about how do I predict the color or the type of the node. So if you are a telecom and you want to predict which of your customers are likely to leave your network, that's an example of a node classification task. You can do link prediction task, which means you try to predict whether 2 nodes in the network will be connected. An example of that could be friend recommendation engine in a social network. You can also do things at the level of sets of nodes where the goal is to identify, let's say, modules in a given network, or what is called community detection. This is something biologists really like to do because they want to understand what are the functional modules inside human cells. And of course, you can then start thinking about doing things at the level of entire networks in order to be able to compare them and measure similarities between them. But in all these types of cases, you have this big problem, which is about how do I capture the structure of the network, right? Nodes have certain properties. We know how to capture those in a set of features. But what is very, very hard is how do I capture the structure of the network? So an example here is, this is an example of a node classification task. The gray nodes need to be colored either with orange or violet. What is the rule that colors these nodes? And the rule depends on the shape or the structure of the network around a given node. And traditionally, a lot of work has been put into identifying features, characteristics that allows us to describe what is the structure of the network around a given node. And of course, what we would like to do is we'd like to kind of take advantage of the deep learning revolution, where hopefully, we'll devise this type of neural network where on the left a graph comes in, and after a few layers on the right, beautiful, happy predictions come out. And of course, these predictions, as I said, could be at the level of nodes, could be at the level of pairs of nodes links, or at the level of entire subgraphs or entire graphs. But the question is, how could we do that? And what I would like to claim here is that the basically modern deep learning toolbox is designed to work with simple data types. So it's kind of specialized to work with simple data types, essentially sequences and grids, right? If we think about images, they are essentially fixed size two-dimensional grids, two-dimensional lattices. And we know how to resize them, and they are all the same size, and we know where is up and where is down, and we can work with that. And even if we think about, let's say, text or speech, it's a sequence, right? So it has this nice linear structure, so we can exploit that linear structure in terms of, let's say, sliding windows so that we can make predictions and model it. But if you think about graphs, natural graphs are much more complex than lattices or chain graphs, right? They have arbitrary size. We don't know how to resize them. They have complex topological structures, and they have no spatial locality like grids, right? It's not clear where is top left corner of a graph and where is a bottom left corner of a graph. And of course, what is even more interesting is there is kind of no reference point, no ordering on the nodes, and these structures can often be dynamic and have multimodal features attached to them. So the question is, how could we generalize our deep learning toolbox to this type of data? So what I want to talk about in this talk is our approach to this, which is an instance of a broader class of models called graph neural networks. So let's start thinking about how could we apply these things, or how could we develop methods that work on graphs. So a first simple idea would be, that's kind of a bad idea, but I want to show it to you, is that you could think of taking the adjacency matrix, right, that captures the structure of the graph, and pump that through your neural network, right? So for example, if I have the graph on the left, that graph on 5 nodes, I show you an example of an adjacency matrix, which is basically a matrix of zeros and ones, where for every row and column denotes a node, and at a given xy position, I have a value of 1 if node x connects to the node y. And in this case, let's also assume that every node has, let's say, 2 binary features attached to them. So I could think of taking the lines from my adjacency matrix and using those as inputs into my deep neural network so that at the end I can, let's say, predict something about each node. And if you think about this, this won't really work. First, the size of the model, the number of parameters, is bigger than the size of the graph. So for a bigger graph, I need a bigger model. It's not applicable to graphs of different sizes. And if I reorder the nodes, if I number or enumerate the nodes in a different order, this thing won't work, right? So what can we do? What we can do is to kind of take this intuition from the computer vision, where the idea is that I have this convolutional operator and I somehow want to slide it over my graph. I have the and do computations over it. Right, so the question is, how would I do this with a graph, right? Like if I have a complex network like I showed you below, and I want to define now some kind of sliding window over it, it's kind of not clear how can I slide that window. It's not clear what is a stride length. It's not clear how can I do that, right? And here is an idea now how this can be done and how essentially convolutions can be generalized to work with complex data like graphs. And essentially the idea is that the network structure, let's say the social network structure, will define the computation graph, right? So the structure of the neural network is defined by the social network. So what this means is that if we want to compute something for the red node I there in the center, if we want to make a prediction about it, what we are going to do is we are going to look at its neighbors and the neighbors of neighbors, and we are going to create a computation graph out of this network structure. And then we are going to learn how to propagate and aggregate information across this computation graph to make a prediction about node I. So what does this mean? How would we do that? So the way to think of this is, if you think of an example here, I have a little network on the left, and the structure of the neural network centered at the node A on the right. And you notice how the structure of this neural network is such that node A gets information from nodes B, C, and D, because in the network on the left, it has the neighbors B, C, and D. And for example, the node C here, it has neighbors A, B, E, and F, because C has neighbors A, B, E, and F, right? So for every node in the network, we'll have a different neural network structure or a different computation graph, right? And this means that now this type of computation graph tells us how the information can be aggregated from the farther parts of the network in order to compute or make a prediction about the node A. What is interesting from kind of traditional neural network approaches is now that every node defines its own computation graph. So potentially every node in the network will have a different computation graph, right? I show you down here the example on the left is for node A. For example, this is node D, the blue node. It has a very skinny computation graph. And for example, the node C here, the green node, has a very kind of high fan-out computation graph because this node has a high degree and a lot of neighbors in the original network, right? So every node will define its own computation graph. So now what we need to do is we need to now learn how to define a learning problem and aggregate and transform the information that's coming from the neighbors and passed through this neural network. Here, I show you only 2 layers, but of course you could go farther out in the network and make these networks deeper if you would like. And this is kind of the only equation I have in my slide, but essentially this tries to give you the idea about how the architecture looks like, right? On the far right, you take in the base features of the nodes, their properties here on the right, and then every box is essentially a little neural network that either takes the information and transforms it, or takes the information from all the neighbors and aggregates it together. So all we have to do is define 2 functions, define a function that combines the information, and define a function that aggregates the information. And what I show you in the equation below is how this can be done over, let's say, 1 layer of the network, where essentially to compute the representation of the parent node A at level k plus 1, all you have to do is you take A's representation at level k, and you transform it, and then you also go over the neighbors of this node A, you take their representation at level k, transform it, and then concatenate the 2 together. And that's your representation at the next level, and you can learn how to propagate this throughout the network. Of course, if every node has a different computation graph, then it kind of doesn't seem we'll be able to learn parameters of this propagation. So what you assume is that these aggregation and transformation parameters are shared across all different neural networks. Why is this elegant is because now it means your models actually have a small number of parameters or a parameters that is independent of the graph size. And it also allows you now to use various kinds of loss functions for the downstream prediction tasks in terms of either making node classifications, link predictions, and things like that. So what I show you here is essentially at the bottom is how are we assuming this parameter sharing is happening, is that essentially these boxes are parameterized. These are the operators, aggregations, and transformations, and they are shared across all computation graphs in the same graph. Why is this also cool is because it has this inductive capability, and it allows us to generalize to the nodes we have never seen, and it allows us to generalize across networks that we have never seen during training, right? So if our graph is evolving over time, as I try to show here with this new violet node appearing in the graph, even after we have trained our model, all we have to do is create a computation graph for that node, and we are ready to make a prediction. So essentially, if we think of having a set of nodes and a set of computation graph, we can always train on a subset of computation graphs and make predictions on some other set of computation graphs that can come from the same graph or can come from a different graph. So this is what I wanted to say about the core idea and the theory. And what I want to do in the next 15 minutes is to give you examples of 3 applications of how this technology can be used in the real world. So the first one is actually a system we have in production at Pinterest, and it's the main recommender engine for pins at Pinterest. Okay. So here is how this thing works, right? So the system is called PinSAGE, and it's essentially a graph neural network like I explained you before. And the idea here is that we want to generate embeddings of nodes in this large-scale Pinterest object graph that has billions of images. And the idea is that kind of doing computer vision on individual images by itself is very hard, and once you have billions of images, it's very easy to make silly mistakes. It's very easy to confuse a garden fence with a bed rail. It's very easy to confuse ground meat and soil, and things like that, right? But because Pinterest is essentially a human curated graph, we have a lot of graph information that allows us to learn how to borrow information from nearby images, and this way not make, let's say, silly mistakes. And this is very useful for services like related pins, search, product recommendations in shopping, ad recommendations for advertising, and so on. So now, first thing I need to tell you is, what's the graph? Pinterest is essentially a human curated graph where people take images and they collect these images into collections called boards. So it's a huge bipartite graph of billions of images that have been independently categorized or classified into boards created by its users. And the use case is generally that somebody is, let's say, in the market for a good, interesting jacket, and they would go around Pinterest and identify jackets they like, and they would save them into a board, into this collection. And then somebody else is in the market for a nice modern reading chair, so they would again look through the website, identify reading chairs they like, and save them into this graph. And this would be now creating this bipartite graph between the images on the top and these collections of images at the bottom. So what do we want to do? Based on users' interaction data, we essentially want to learn how to aggregate information from nearby images in the graph to develop an embedding, basically a set of coordinates for every image, such that the images that are related are closer in the embedding space than images that are not related. So we can collect a lot of user interaction data where when a user is looking at a cake and they save another cake into the same board versus, let's say, some random pin like this sweater, which generally is not saved to the same board as cakes. Of course, this graph is massive. It has about 3 billion images, another 3 billion boards, and even after we prune a lot of edges out of it, it's still 20 billion edges. And of course, every image in this graph is annotated both with the rich textual features as well as the image itself. And what we would like to do, our goal, our task is, as I said, is to learn how to generate coordinates for every image so that the distance between images that are related is smaller than the images that are not related. And based on user interaction data, we know what is related, but kind of we don't know what is not related. So we generally would take, let's say, random images and say, those are not related. And if you train your model this way, it doesn't work so well. And the reason it doesn't work so well, because what we really care about when we have this in production is that you identify the closest 100 images. And among the closest 100 has to be a related image. And we don't really care what happens at the rank 10 million, 1 billion, or 2 billion. We couldn't care less about that, right? And if we are training our system to distinguish positive examples from these random negative examples, then it's too easy. It's too easy to distinguish a cottage from a thank you card. So what we have is this training procedure where we identify this notion of hard negative examples. Here, for example, it would be a happy birthday card that visually looks very similar to a thank you card, but it's in some sense totally unrelated, and it's a bad recommendation. And by giving these harder and harder examples to our learner, we're essentially able to learn how to sort 3 billion objects and make sure that the relevant object is the most closest 100, right? So we are kind of learning to a very, very high precision in this embedding space. And to show you how well this works, it actually works amazingly well. I give you examples in terms of mean reciprocal rank. Higher is better. Annotation is a textual-based recommender engine that would look at how do the textual annotations, the title of the image, how does that match? Visual is based on the sole visual embeddings, and then the PinSAGE basically takes this visual and textual information and learns how to aggregate it across the graph to get a huge gain. And just to give you one more example, how would this look like? On the left is a query image, and on the right I show you 3 closest images. If you do visual comparison, right, these are some, I don't know, California settlers who just cut down a big tree. Then, you know, in the visual space, you have examples like some farmers and soldiers and so on, but all kind of black and white historic photos. If you do textual matching, it actually gives you things from forests, which is good, but it doesn't have the resolution to be able to do that. But our system actually allows you to identify images that are about historical images about people cutting down trees. So that's the first thing I wanted to show. Now, the second thing, a very different area. So this is about computational drug discovery and really thinking about how could we predict side effects of drugs. So here's the use case. The use case is that many patients take multiple drugs and this to treat complex diseases. And as people take multiple drugs, kind of drugs can interact with each other and very unexpected side effects may occur. And of course, because there is too many drugs on the market, generally when a drug trial is done, it's only a patient takes only that drug and they see what is happening. But it's impossible to kind of now test all possible combinations of drugs. And if you look at in United States, people between 70 and 80, about half of them is on at least 5 drugs, and there is many patients who are taking 20 drugs at the same time. And the question is, if you are taking a combination of drugs, can we predict what kind of undesirable side effects can occur? And the way we are going to do this, we are going to do this as a graph problem. So the way we are going to approach this is that we'll create a network of 2 types of nodes, a set of proteins, those are the circles, and a set of drugs, those are the triangles. And proteins are the molecules in our bodies that come together physically to interact with each other and do functions in our cells. So that's almost like the map how the life works. And what the drugs are, drugs target or change behavior of proteins. So that's why there are also links between the triangles and the circles, because each drug targets certain proteins. And then the last set of links we have are the links between the drugs, and 2 drugs are connected if they cause a side effect. Each link is labeled by one of 966 different types, because that's the number of different side effects that we are trying to model. Okay, so now what we did is, in some sense, we will think of this as a link prediction task between the triangle nodes in the graph, where the link can be of one or more of the 966 different types. So the task will be the following. We will try to learn the representation, the coordinates for every drug node, for every triangle. This will be the encoder. And then the decoder will take the coordinates or the representations of the two drug nodes and will try to predict the probability of a link for all the 966 different link types, different side effect types. Again, the way we are going to define our computational architecture is defined by the graph structure itself. So we will have if I show you a graph for this graph's drug C here on the left, then on the right I show you the computation graph for the drug, essentially across different relationship types. So side effect type R1, R2, we will have a different computational architecture, and then we'll have another architecture here at the bottom that takes the information from the proteins and learns how to aggregate this. And we will stack these two layers one after another. So this is how the encoder will look like. And now how does decoder look like? We take a pair of nodes. Here is the neural networks for the pairs of nodes, their representations that we learn. And then we have a decoder that is essentially a tensor factorized model that will return us 966 different probabilities. For every side effect type, we will get the probability that that pair of drug interacts with that particular side effect type. And of course, now we can go and train this in an end-to-end way. We can do back propagation from the right all the way back to the left to learn the parameters of the model. If you ask how well does this work, we see that it beats current state of the art by 36% on the average in average precision at 50. And what is maybe even more interesting is we asked our model, we took the data, we trained the model, and then we asked the model, what are the side effect types that you are, between pairs of drugs that you are most sure about? And here are the 10 side effect types that, between 10 drugs that our model is most sure about. And what we then did is we said, okay, these are the predictions that are not in our data. Can we go into the medical literature and see if there is any evidence that any of this might be true? And what is interesting is that actually for 5 out of these 10, we have already found evidence, basically clinical reports that are stating that they have observed these types of side effects for these types of drugs, right? So these are novel predictions, not known, not recorded in any database. They just kind of appear in random clinical reports, but 5 out of 10 have already been confirmed in the last few years. So that's application number 2. And I have time for application number 3. So this is about taking this idea of heterogeneous graphs, but really think about knowledge graphs and not just doing simple link prediction, but can we do more complex logical reasoning in these types of networks? And I'll give you 2 examples of what do I mean by a knowledge graph. For example, from the previous case when we are doing this side effect prediction, we can essentially take all the knowledge we have about human biology and compose it into this heterogeneous network where we have a set of proteins. There's around 20,000 proteins in our bodies. Everything we know about diseases. There's about 14,000 known diseases. There's around 11,000 drugs. Drugs treat diseases. Drugs target proteins. Diseases are associated with proteins. Drugs can cause side effects. We have those, and then we also know a lot about how proteins interact with each other in terms of 7 different interaction types, and then there is also an ontology of biological processes that is kind of on top of that biological graph. So that's one way how you can kind of integrate information. And then on the right, I give you an example of an online community. So this is essentially, you could think of this as a knowledge graph of Reddit, where you have users. Users create posts. Posts can be also commented on, upvoted or downvoted. Posts contain words. Posts belong to communities, and users can follow or subscribe communities. And we have about 500,000 users, 150,000 posts, 250,000 words, and let's say a sample of 100 communities, right? And you can see how you could make these things more complex. So now, if we have this type of knowledge graphs, we could start asking ourselves, can we make complex predictions over them? So for example, could I say, can you predict communities C in which a given user U is likely to upvote a post? And the way you can think of this, you can write it down in logic, but you can also write it down in terms of this query graph, where it basically says, I wanna predict, I wanna go from a given user, I wanna go over the relationship type of upvote to a given post, and then I wanna go from a relationship type belongs to from the post to the community. So the way traditionally this has been solved was that you would take your knowledge graph, you have this query template, and now you try to do pattern matching. And you are kind of brute force, do pattern matching, and you see in what all cases would this query graph be able to be matched on my underlying knowledge graph. And if your knowledge graphs are small and super clean and completely labeled, then this may work. But real-world knowledge graphs are noisy, have a lot of unobserved, incomplete information. They are huge, and queries might be huge. So in practice, this kind of pattern matching approach doesn't really scale and doesn't really work. And if you have kind of some errors or some missing data, there is no way that this type of pattern matching approach would be able to resolve that. Of course, what you could do is you could build a machine learning system that will predict all the missing relationships and estimate their probabilities, and then you could reside back to the pattern matching. But if you do that, you kind of haven't done anything, because now you made your graph even denser, so it has more relationships, so your pattern matching has to do even more work, so it's kind of even worse. And errors compound on top of each other. So our approach to this problem is very different. Our approach is to do this reasoning in the Euclidean space. So the way we do this is to say, let's try to answer a complex logical query. Here, for example, now going back to biology, imagine I want to predict drugs C that are likely to target proteins P associated with two concrete diseases, D1 and D2. Right? So this particular query could be decomposed in this type of query graph. And what we will do is we built a machine learning system that learns how to embed the nodes of this graph into the embedding space, and then for every of the logical operations, learns an equivalent of a spatial operation. So what this would mean, that if you want to execute this particular query in the embedding space, you start with the positions of the two known diseases, ZD1 and ZD2. You apply the operator associated with, here denoted by the green line. This kind of moves you into some other point in the space. From D1, it moves you to another place. From D2, it moves you to another place. Now you are applying a different spatial operator called intersection that takes these 2 points and maps them into another different point, here noted as I. And then in the last step, you are now applying a different spatial logical operator called targets that goes from I to the position Q in the space. And the way you now answer the query is to simply say, what are the nearest neighbor of this node Q in the space? And whatever is close to it, that's the answer to your query. And the benefit of this is that you can train this on large scale. You have to do it jointly. You have to learn the node embeddings as well as the spatial operators together. And what is interesting is that when you say, how accurately can I basically now answer these queries as simple nearest neighbor lookups in this embedding space, you can do that very, 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 very effectively. So what I'm showing you down here is examples of different query structures, like, for example, 3-hop link prediction, or these more complex things, and the AUC score in terms of how accurate answers are we giving. And especially for the biological use case, we are able to do that with 90+% AUC. And for the social use case, which is more noisy, we are still doing quite well, between 90 and, let's say, 65. So this is the last application I wanted to tell you. So just to summarize, right? I want to give you kind of ideas and how deep learning, representation learning can be applied more broadly beyond kind of simple data types, meaning grids and sequences. And this kind of brings us to new frontiers of how classical neural networks learn and how they are able to aggregate information. And of course, there's many real-world problems where you can now take this and apply it to problems at the level of nodes, pairs of nodes, or subsets of nodes. And I would say, to conclude, if there is something we have learned in the last 2-3 years, is that this representation learning paradigm can be extended very successfully to graphs, that no structural feature engineering is necessary. It allows us to effectively combine attribute data with the network structure information, leads to state-of-the-art results in a number of domains and tasks. And one important thing is that because we can use this end-to-end training, it tends to beat this kind of human-engineered multi-stage approaches by a lot. So with this, I'm done. Thank you very much.
I think maybe we could take 1 or 2 questions, but maybe if we move to the other microphone so that we can set up the next speaker while you answer some questions. Does anybody have a question for Professor Leskovec?
No, thank you. Amit Pirosh, IBM. So this is really fascinating working with very large graphs like this. So the point here is that as you do your reasoning, we have been using like iterative algorithms to do it or do deep learning. The underlying graph changes because you keep adding new links at least over there. Then how do you iterate over the entire thing? Because you got an graph in and then you got thing, but you have to iterate back.
If the graph is changing or if you are adding new knowledge to the graph, that's no problem because you can keep refining your operators and your embeddings as time goes on. So you could easily, if you are asking queries, getting answers, and then getting some information whether those queries were correctly answered or not, you can easily incorporate it into the training loop, and you keep refining both the embeddings and the operators you are learning. So that can be very naturally incorporated. Good. Okay.
Thank you very much.
Thank you very much.